In today's lesson, we're going to learn how to integrate rational functions by partial fractions. When we're integrating using partial fractions, we try to take a rational function and break it up into simpler fractions called partial fractions. Then we can integrate these partial fractions. So looking at this question, we had this rational function right here. It was broken up into these two partial fractions, and then we integrated each of those parts to get our final answer. The key is being able to go from here to here. So we're going to spend the first part of 5.2 just on converting a rational to partial fractions. So how could we change x plus 5 into partial fractions? Or sorry, how could we change x plus 5 over x squared plus x minus 2 into partial fractions? Well, what we could do, first of all, is we could say that x plus 5 over, and I could factor the denominator as the following. So now, if we have two factors in our denominator, so that really means that we have something over our first factor in our denominator plus something over the second factor in our denominator. So if we got a common denominator here, we could get back to what we started with. So now I am going to multiply everything by x squared, by x plus 2 and x plus 1. So I'm going to distribute that to all three of these terms. And when I multiply x plus 2, x plus 1 by this first term, the denominator is going to cancel out with that, so I'm just going to be left with x plus 5. When I multiply this term by x plus 2, x plus 1, I'll be left with a times x plus 1. And when I multiply that onto b over x minus 1, I'd be left with b times x plus 2. So now my goal is to try to figure out what is a and what is b. So let's first of all try to make some substitutions for x here. Well, it makes sense to first of all let x be negative 1, because if I put a negative 1 in, I get negative 1 plus 5 is equal to negative 1 plus 1 plus b times, or plus b negative 1 plus 2. So therefore I end up getting 4 is equal to 0 times anything is 0, and this becomes b times 1, which is just b. So therefore we know that b is equal to 4. Then if I let x equal negative 2, I get negative 2 plus 5 is going to equal a negative 2 plus 1 plus b negative 2 plus 2. This time, this guy is going to be 0, so that drops off. And I'm left with 3 is equal to negative a. And if I divide both sides by negative 1, I get a is equal to negative 3. So therefore, as partial fractions, I could put negative 3 in here, and I could put 4 in there, and therefore I've taken this, and I've written it as its two partial fractions. So that's kind of the first process we have to be able to do in order to integrate these rational functions. Now there are a few things to consider when trying to express a function as a sum of simpler fractions. First of all, if the degree of the numerator is less than the degree of the denominator, then the function can be expressed as a sum of fractions, just like we did in the previous question. If the degree of the numerator is greater than or equal to the degree of the denominator, then we need to do some long division to get a polynomial plus a rational function that can be integrated. Expressing as a sum of partial fractions. Case number 1, if our denominator qx is a product of distinct linear factors, so all of these factors down here are linear, then it's just going to be a constant over the first factor plus a constant over the second factor of the denominator plus a constant over the third. That one's pretty straightforward. If q of x is a product of linear factors, some of which are repeated, then it's a little bit more challenging. So I would have to go a over x, then b over x squared, c over x minus 1, d over x minus 1 squared, and then e over x minus 1 cubed. So that would be broken up into 5 fractions. If q of x has quadratic factors that cannot be reduced, then this one is linear. So for this one, it's just a over x minus 2. But this is a quadratic in the bottom, so we have to put a linear on top. So it's going to be bx plus c over x squared plus 1, and then dx plus e over x squared plus 4. Now, we don't get into a lot of these cases, so once we get to the specific examples, we may reference a few of these, but don't get too panicked about some of all these different rules right now. Q of x, the denominator has repeated quadratic factors, so we notice we have repeated factors right here. So first of all, again, we're going to have a over x, b over x minus 1. This is a quadratic factor, so my numerator is a linear, so cx plus d over x squared plus x minus 1. And then ex plus f over x squared plus 1, gx plus h over x squared plus 1 squared, and ix plus j over x squared plus 1 cubed. Now, let's get to some of the rewriting as a sum of fractions. So if I have 1 over x squared minus x minus 4, well, first thing, I know that this factors into x minus 3, x plus 3, x minus 4. So this would be a over x plus 3 plus b over x minus 4. And we won't worry about solving for a and b right now. We're just going to break this up into its partial fractions. So if I have something like this, first thing I'm going to do is I'm going to factor an x out of the bottom, and that would leave me with an x squared minus 5x plus 6, which then factors into x minus 3 and x minus 2. So these are all distinct linear factors, so it's going to be a over the first factor plus b over the second factor plus c over the third factor. Now this one here, notice we have a repeated factor, we have x cubed, and we have a binomial. So when I write this, it's going to be a over x, and I have to go b over x squared plus c over x cubed. So now I've written all the possibilities for that one. And this is a binomial, so therefore it's going to be a linear, and my next variable would be dx plus e over my quadratic factor in the denominator of x squared plus 1. And there would be my partial fractions. Now notice in this one, the degree of the numerator is bigger than the degree of the denominator, so you should be putting a little star beside this one. Because in this particular case, I have to do some long division. So I have to take my denominator, which is x squared minus 2x plus 1, and I have to divide it into x cubed. So if I take x cubed minus 2x plus 1, what do I have to multiply x squared by to get x cubed? Well, that's going to be an x. And then I multiply, so x times x squared is going to be x cubed. X times negative 2x is negative 2x squared. And x times 1 is going to be x. So really there is a 0x squared here and a 0x. Now I'm going to subtract this row from this row, or you could change this to a minus and change all the signs, and then we could add. So these are going to cancel. This would become a 2x squared. This is going to be minus x. And then you can ask yourself, what do you have to multiply x squared by to get 2x squared? Well, that's going to be a plus 2. So I multiply that. I get 2x squared minus 4x plus 2. Draw the line, change the signs, and we'll add these. So those cancel. I'll be left with a 3x subtract 2. So, therefore, when I rewrite this, okay, I have a x cubed over x squared minus 2x plus 1 is really going to equal my quotient, which is x plus 2, plus my remainder, which is 3x minus 2 over my divisor of x squared minus 2x plus 1. Now, we can go a little bit further, because for this part, I can now apply the partial fractions. So I could rewrite 3x minus 2, and this denominator is x minus 1 squared. So this is going to work out to be, well, the x plus 2 just tags along. Then it's going to be a over x minus 1 plus b over x minus 1 squared. And there would be all of your partial fractions for this one. Okay, the last one, we want to write this as a sum of fractions. So it's going to be a over x, which is linear. I have another linear of x plus 2. Now I have a parabola or a quadratic, so it's going to be cx plus d over x squared plus 2 plus ex plus f over just x squared plus 5, and then gx plus h over x squared plus 5 all squared. And those would be the partial fractions. Okay, I'm going to give you a few to practice. So again, all I want you to do is write them as their partial fractions. Okay, so here are the 6 that I want you to do. Okay, so number 1 is 1 over x minus 1 times x plus 2. Second one is x squared minus or plus 3x minus 4 over 2x minus 1 squared times 2x plus 3. The third one is 1 over x to the 4th minus x cubed. The fourth one is x squared plus 1 over x squared minus 1. The fifth one is x squared minus 2 all over x times x squared plus 2. And the last one is x to the 4th plus x squared plus 1 all over x squared plus 1 times x squared plus 4 squared. So the only one that you need to do long division on, obviously, is this one here, because here the degrees are equal. In all the other cases, if you were to expand the denominators, the degree of the denominator would be larger than the degree of the numerator. So give these a whirl, okay? And if you have any questions, send me an email, and I can go over any of those with you if you'd like.